Now hold that thought, because it gets stranger. There is a distance beyond which no light has ever had time to reach us at all. Not because nothing is there, because the universe is only 13.8 billion years old, and light only moves so fast, and some regions of space have simply never had enough time to send us a signal. We call the boundary of that region the edge of the observable universe. It sits about 46 billion light-years out in every direction. Past that line, our instruments go dark. Our telescopes see nothing, not empty space, nothing. The information has not arrived yet, and some of it never will. Most people hear that and picture an edge, a wall, a place where the universe stops and something else begins. That instinct is wrong, and understanding why it is wrong is the whole point of what follows. The observable universe is not the universe. It is a bubble, a lit room inside a house we cannot see the walls of. Everything we have ever mapped, every galaxy, every black hole, every signal we have ever pulled out of the sky, fits inside that bubble. And the bubble is almost certainly surrounded by something incomprehensibly larger, something we cannot measure, cannot reach, and in some cases, cannot even theorize about cleanly. What fills the dark beyond that edge is one of the genuinely open questions in all of science. Here is what makes this specific question different from most. When physicists say they do not know something, they usually mean the data is incomplete, the instruments are not sensitive enough, the math is still being worked out. Give it time, they say. This is not quite that. The boundary of the observable universe is not a technology problem. It is a geometry problem. It is a speed of light problem. There are regions of space that are receding from us faster than any signal could ever cross the gap. Regions whose secrets are not hidden behind better telescopes, but behind the fundamental physics of how space expands. We are not going to close that gap by building bigger instruments. The gap is closing us. The question is not whether something is out there past the edge of everything we can see. The question is what? The observable universe has a radius of about 46 billion light-years, and almost nothing about that number is intuitive. Start with the age. The universe is roughly 13.8 billion years old. That is how long it has been since the Big Bang. So you might expect the farthest light we can possibly receive to have traveled 13.8 billion light-years to reach us. 1 light-year per year. Simple math, clean answer. Except that is not how it works. The universe has been expanding the entire time that light was traveling through it. Space itself was stretching. A photon that left some distant region 13.8 billion years ago did not travel through static space. It traveled through space that was pulling apart underneath it, and the source of that photon has been moving away the whole time. By the time the light finally arrives here, the object that sent it is now roughly 46 billion light-years away. Not 13.8, 46. The light caught up, but the source did not wait around. This confuses people, and it should. It seems to suggest that something moved 46 billion light-years in 13.8 billion years, which would mean it was traveling faster than light. It was not. The object itself never moved faster than light through space. Space simply expanded, carrying the object with it, the way dots on the surface of a balloon get farther apart when you inflate it, without any dot moving across the surface. There is no speed limit on how fast space can expand. The light speed limit applies to objects moving through space, not to space itself stretching. So when you hear 46 billion light years, that is not a contradiction. That is expansion doing what expansion does. Here is the concrete picture. The observable universe is a sphere. You are at the center. Every direction you look, the sphere extends outward about 46 billion light years before hitting the boundary, the point beyond which light simply has not had time to reach us yet. Everything inside that sphere is, in principle, observable. A telescope good enough could see it. Everything outside the sphere is not hidden behind a wall or blocked by anything physical. It just has not sent us any information yet, because the universe is not old enough for that information to have arrived. The boundary is a time problem, not a space problem. Now here is the part that tends to stop people cold. You are not special. There is nothing unique about the fact that you are at the center of your observable universe. Every single point in the cosmos is at the center of its own observable sphere, equally large, extending 46 billion light years in every direction from wherever it sits. An observer in a galaxy 10 billion light years from here has their own sphere, entirely centered on themselves, and it contains billions of galaxies we will never see, in every direction around that observer. Our spheres overlap. There is a region we both can see, but their sphere extends far past our horizon into territory completely invisible to us, just as ours extends far past their horizon into territory invisible to them. No location in the universe has a privileged view. Every observer is surrounded by the same kind of bubble. What changes is only what is inside each particular bubble. Scale helps here, even if scale eventually stops working the way your brain wants it to. Our entire Milky Way galaxy is about 100,000 light years across. The observable universe is roughly 930,000 Milky Ways laid end to end in any direction from where you are standing. The nearest large galaxy to us, Andromeda, sits about 2.5 million light years away. Inside the observable universe, there are an estimated 2 trillion galaxies, each containing hundreds of billions of stars, spread across a volume so large that the number stops behaving like a number and starts behaving like a symbol. And all of that, every galaxy, every star, every atom in that entire sphere, sits inside the lit room. The dark house around it is larger still. What sits at the edge of the observable sphere is not a wall. It is not darkness exactly. What you are seeing when you look toward the cosmic horizon is old light. Light from an era when the universe was dense and hot and opaque, before the first stars existed. The farthest back our instruments can see, the boundary where light finally stops reaching us, corresponds to roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and for light to travel freely for the first time. Before that moment, the universe was like a fog. Photons could not get through, so even if we built a perfect telescope with unlimited sensitivity, there is a wall of fog at that distance, and behind the fog, nothing visible. But the fog is not the edge of space. It is just the edge of what light can show us. Space continues past the fog. The Big Bang happened everywhere. The fog is thick in every direction at the same distance, which means the universe, whatever it looks like beyond it, goes on. The key word in everything here is time. Every layer of the observable universe you look at is a layer of the past. A galaxy 500 million light years away looks the way it looked 500 million years ago. A galaxy 10 billion light years away looks the way it looked 10 billion years ago. When you reach the cosmic horizon, you are looking at the universe as it was nearly 13.8 billion years ago. The boundary is not a place, it is a timestamp. And because the universe is the same age everywhere, the Big Bang happened at the same time everywhere. Every observer in the cosmos hits that same timestamp at the same distance from themselves. The edge of the observable universe is not a wall you could fly toward and eventually reach. It is a time limit, and it follows you wherever you go. To picture what the edge actually is, you have to resist the instinct to imagine it as a surface, a line, or a place where something stops. That instinct is almost impossible to shake. Every boundary you have ever encountered in your life has been a physical thing. A wall, a shoreline, a fence. The edge of the observable universe is none of those. There is no barrier out there, no wall, no sign. If you could travel toward it at any speed you wanted, you would pass through it and feel nothing, because there is nothing there to feel. What looks like an edge from where we stand is entirely a consequence of two facts that have nothing to do with space running out. Light travels at a fixed speed. The universe has a finite age. Put those two things together and you get a horizon, not because space ends, but because time did. Think about what that actually means. The Big Bang happened roughly 13.8 billion years ago. In the time since then, light traveling toward us from any direction has had 13.8 billion years to make the trip. That sets a hard limit on how far back we can see. Any object that was too far away when the universe began for its light to have reached us, yet is invisible to us, not because it does not exist, but because the signal has not arrived. The observable universe is not the full universe. It is the portion of the universe whose light has had time to reach us so far. The edge is a deadline, not a destination. Now here is where it gets strange. That exact same logic applies to every other location in the universe equally. There is nothing special about where we are sitting. An alien civilization living in a galaxy 40 billion light years from here would have their own observable sphere, centered on themselves, with a radius of roughly 46 billion light years in every direction. Their bubble would be just as large as ours. And here is the part worth sitting with. Ours and theirs would have no overlap. The two observable spheres would be entirely separate regions of space, with no single galaxy appearing in both. Two civilizations, each surrounded by an enormous observable universe, each completely blind to what the other can see. There is no master map. There is no privileged viewpoint from which you can see it all. Every observer gets their own window, and no two windows look out on exactly the same view. This also means the edge is not a fixed feature of the universe. It is fixed to you. It follows you. If you move to a different galaxy, your observable sphere would move with you, centered on your new location. The region behind you would slowly pass out of your view, and a new region ahead of you would inch into it. The horizon is not a place in space. It is a radius around wherever you happen to be, set by the speed of light and the age of the universe, recalculated at every position. It was also smaller in the past. When the universe was 1 billion years old, an observer anywhere in it could only see light that had been traveling for 1 billion years. The observable universe at that moment was dramatically smaller than it is today. Every day that passes, more light from further away has had time to reach us, and the horizon expands slightly. You might expect this to be purely good news. More universe revealed over time. But expansion complicates that story in ways that come up later. The simple version is that the horizon is growing, but not fast enough to outrun certain parts of what lies beyond it. What the horizon is not, and this is worth being direct about, is evidence that space stops. Nothing in the physics of the observable universe suggests that matter, energy, or space itself ceases to exist at the boundary of what we can detect. The universe did not draw a circle around us. We drew the circle ourselves by measuring the speed of light and counting the years since the beginning. The boundary is ours. It is a feature of our situation, not a feature of reality. The disturbing implication of all this takes a moment to settle in. When most people use the word universe, they mean everything. All of space, all of matter, everything that exists. But in practice, what scientists can actually study, measure, test, and map is only the observable universe. Our bubble, our 46 billion light-year sphere. Everything said about the composition of the universe, the distribution of galaxies, the large-scale structure of space, is said on the basis of that bubble alone. The observable universe is the only universe we have access to. And the observable universe is almost certainly a small fraction of the actual universe, whatever that turns out to mean. Calling the observable universe the universe is like assuming the town you grew up in is the only town that exists because you have never been able to leave it. The horizon is a limit on information, not a limit on existence. Out past the farthest thing we have ever detected, past the oldest light we have ever measured, space continues on in all directions, filled with whatever it is filled with, completely indifferent to the fact that we cannot see it. That matter does not disappear when it crosses our horizon. Those galaxies do not stop existing when their light takes too long to reach us. The universe did not end at the boundary of our observable sphere. We just ran out of time to see what came next. In every direction in the sky, coming from the farthest distances any instrument has ever probed, there is a faint glow. Not light from a star, not light from a galaxy. Something older than either of those things. It comes from everywhere at once, uniform and ancient, and it has been traveling toward you since before the Earth existed. Astronomers call it the cosmic microwave background, and it is the closest thing we have to a photograph of the early universe. More than that, it is a message. And once you know what it says, the question of what lies past the edge starts to look a little less unanswerable. To understand what the CMB actually is, you have to go back to the first 380,000 years after the Big Bang. The universe at that point was not dark and empty the way it is today. It was a dense, ferociously hot plasma, something like the interior of a star stretched across all of space. Photons, the particles that carry light, were constantly colliding with electrons and getting scattered. They couldn't travel in straight lines. The universe was opaque, like trying to see through a wall of fog so thick that light simply bounced around inside it without going anywhere. Then, as the universe expanded and cooled, something changed. The temperature dropped enough that electrons could finally bind to protons and form neutral hydrogen atoms. When that happened, the fog lifted. For the first time, photons could travel freely without being scattered. Light escaped. The universe became transparent. That moment is called recombination, and the light that was released at that moment is still traveling. It is what we detect as the CMB. What the CMB looks like when you map it across the full sky is one of the most striking images in science. It is almost perfectly uniform. In every direction, the temperature of that ancient radiation reads at about 2.7 degrees above absolute zero. Turn the telescope north, south, east, west, it doesn't matter. The number barely changes. For the universe to look that consistent from every angle we can check, the conditions at the time of recombination had to be nearly identical across enormous distances. Distances larger than anything that could have been in contact with each other through ordinary cause and effect. That uniformity is not something you get by accident. It is telling you something deep about the structure of space itself. Here is where it connects to the question driving this whole conversation. The CMB is coming to us from roughly the edge of what we can observe. The region that emitted this light sits about 46 billion light-years away in every direction, right at the limit of our particle horizon. When we say the CMB looks the same in every direction, what we are really saying is that the universe, as far out as our instruments can possibly reach, has the same properties everywhere we look. Same temperature, same density, same basic conditions. There is no direction in which the CMB suddenly looks different. No quadrant of the sky where the signal breaks down. No hint that we are approaching some boundary where things start to behave differently. The edge of our observable universe looks, in every direction, exactly like everywhere else. The implication is hard to overstate. If the universe is uniform right up to the edge of what we can see, there is no particular reason to expect it to become something radically different just past that edge. The most straightforward reading of the CMB is that the universe continues beyond our horizon with the same general character it has on this side. More hydrogen, more galaxies, more structure built from the same raw material. Not necessarily identical, but governed by the same physics, shaped by the same forces, distributed with the same rough density. Now, the CMB is not perfectly uniform. That part matters too. When you amplify the tiny temperature differences in the map, variations at the level of about 1 part in 100,000, a pattern emerges. Faint ripples, slight hot spots and cool spots scattered across the sky. These fluctuations were not random noise. They were the imprints of pressure waves moving through the early universe before recombination. Sound waves, in a sense, frozen into the structure of the plasma at the moment the fog lifted. What happened to those fluctuations after recombination is the entire history of cosmic structure. Regions slightly denser than average had a little more gravitational pull. They drew in more matter. Over hundreds of millions of years, those regions became the seeds of the first galaxies. The large-scale structure of the universe you see today, the filaments of galaxies, the walls and the voids between them, all of it traces back to those tiny temperature ripples in the CMB. You are looking at the blueprint of everything that came after. What that means for the question at hand is this: if the same fluctuations exist in the unobservable universe beyond our horizon, and the uniformity of the CMB strongly suggests they do, then the same process of structure formation played out over there. Gravity did the same work. Gas clouds collapsed, stars ignited. Galaxies assembled themselves around dark matter scaffolding the same way they did here. The details would differ, because the specific pattern of fluctuations would differ from place to place. the way two snowstorms produce different snowflakes from the same physical rules. But the broad strokes would be familiar. The CMB is the last thing we can directly observe from close to the edge. Past the surface where it was emitted, our instruments go dark. But that surface gives us one final extraordinary data point about what exists in the territory we cannot reach. It says, same rules, same conditions, same universe. Whatever is past the edge, the CMB is telling us it almost certainly looks a great deal like what we can already see. Here is a number worth sitting with for a moment. Of all the matter and energy in the observable universe, the kind you can actually see makes up roughly 5%. Not 50%, not 20%. 5. Every star you have ever looked at, every galaxy the Hubble telescope has ever photographed, every planet, every asteroid, every cloud of gas, every atom in your body, all of it combined adds up to about 1/20th of what the universe actually contains. The other 95% is something else entirely. Two somethings, in fact, that have almost nothing in common except that we cannot see either of them and we do not fully understand either of them. Astronomers call them dark matter and dark energy, and together they are the invisible majority that runs everything. Dark matter came first, in terms of discovery. The clues showed up in the 1930s, when a Swiss astronomer named Fritz Zwicky was studying a cluster of galaxies and noticed something wrong with the math. The galaxies in the cluster were moving too fast. If you added up all the visible mass, every star, every gas cloud, the gravity it produced was not nearly strong enough to hold the cluster together at those speeds. By any calculation, those galaxies should have flown apart long ago. They hadn't. Something was holding them. Something with mass that he couldn't see. Zwicky called it dunkle materie, dark matter. People mostly ignored him for decades. Then, in the 1970s, an astronomer named Vera Rubin ran into the same problem studying individual galaxies, and this time the evidence was hard to dismiss. Stars at the outer edges of galaxies were orbiting the galactic center just as fast as stars near the middle. That should not happen. If the visible mass were all there was, outer stars should be orbiting much more slowly, the way the outer planets of our solar system orbit the sun more slowly than the inner ones. The fact that they weren't meant there was invisible mass spread throughout and around every galaxy, a vast halo of something with gravity but no light. What is dark matter exactly? The honest answer is that nobody knows. It does not emit light. It does not absorb light. It does not interact with ordinary matter except through gravity. Every particle detector built to catch it has come up empty. Every candidate particle that theorists proposed has been ruled out or remains unconfirmed. It passes through walls, through planets, through you, without leaving a trace. There are roughly 27% worth of it filling the observable universe, threading through every galaxy and galaxy cluster, forming the invisible scaffolding on which the visible universe is built. The large-scale structure of the cosmos, the great web of filaments and walls and voids that shows up in galaxy surveys, is not primarily a structure of stars and gas. It is a structure of dark matter. The galaxies are just the lit parts, like lights strung along a frame you cannot see. The second invisible component is stranger still. Dark energy makes up about 68% of the universe's total content, which means it is the single largest ingredient by a wide margin. It was discovered in 1998 when two independent teams of astronomers were studying distant supernovae to measure how fast the universe was expanding. The expectation was that gravity would be slowing the expansion down over time, that after the initial blast of the Big Bang, things would gradually be pulling back toward each other. What they found instead was the opposite. The expansion was not slowing, it was speeding up. The universe was not coasting, it was accelerating, pushed by something acting against gravity, something filling space itself and growing stronger as space grew larger. Both teams got the Nobel Prize in 2011. The force driving this acceleration got a name: dark energy. What it actually is remains completely unknown. Here is what makes dark energy so unsettling in the context of everything we have been discussing. Dark matter at least behaves like matter. It has mass, it clumps, it pulls things together. You can map it, at least indirectly, by watching how gravity bends light around it. Dark energy doesn't do any of that. It is not a particle. It is not a field in any conventional sense. The leading candidate is something called the cosmological constant, a term Einstein originally added to his equations of general relativity and then famously removed, calling it his greatest blunder. It turns out he may have been right the first time. The cosmological constant is essentially an energy density built into the fabric of empty space. Every cubic centimeter of vacuum, everywhere in the universe, contains a tiny amount of this energy. And because space is expanding, because there is always more space, the total amount of this energy keeps growing. The more it grows, the faster it pushes space apart. When physicists try to calculate what the cosmological constant should be from quantum field theory, they get a number roughly 10 to the power of 120 times larger than what we actually observe. That is the worst prediction in the history of physics by an extraordinary margin. Something is cancelling almost all of it out, leaving just a tiny residual that drives the accelerating expansion. Nobody knows what that cancellation mechanism is. Nobody knows why the residual is the particular value it is. This is not a minor gap in knowledge. It is a foundational mystery sitting at the center of our best theory of the universe. What does any of this have to do with what lies past the edge of everything we can see? More than it might seem. Dark matter shapes the structure of the universe on every scale we can observe. If it extends beyond the cosmic horizon, and there is no reason to think it stops there, then whatever structure exists in the unobservable universe is shaped by the same invisible scaffolding we see here. The web of filaments and voids continues, built on dark matter's skeleton, in regions we will never directly probe. Dark energy, though, does something more directly relevant to the question of the edge itself. Because dark energy is accelerating the expansion of space, it is actively determining how much of the universe will ever be visible to us. It is the engine pulling galaxies past the horizon, placing them permanently beyond reach. The faster space expands, the more rapidly the observable universe is being carved away from the rest of existence. Understanding what lies past the edge requires understanding dark energy, and we are very far from that. Dark energy, which we cannot detect, cannot explain, and can only infer from the motion of things moving away from us, is the dominant force shaping everything that exists, including everything we will never see. Space has a shape, and the shape turns out to matter enormously for what exists beyond the horizon. That might sound strange. Space feels like nothing, like the absence of something rather than a thing in itself. But emptiness has geometry, And that geometry has consequences that reach all the way to the question of whether the universe ever ends. There are three options, three ways space itself can be curved at the largest scales. The first is positive curvature. Picture the surface of a sphere. On a sphere, if you start walking in any direction and you never stop, you eventually come back to where you started. There is no edge, but there is a limit. The sphere is finite and boundless at the same time. A positively curved universe would work the same way. Travel far enough in one direction and, in principle, you arrive back where you launched from. This kind of universe has no wall, no drop-off point, but it has a size. You could, at least theoretically, measure it. The second option is negative curvature. Picture the shape of a saddle or a mountain pass, curving upward in one direction and downward in another. A negatively curved universe bends the other way. Parallel lines spread apart. Triangles have interior angles that add up to less than 180 degrees. This universe is infinite, open, with no center and no edge, expanding outward in every direction forever. The third option is flat. No curvature at all. Parallel lines stay parallel forever, no matter how far they go. Draw a triangle anywhere in flat space, and its angles sum to exactly 180 degrees. Flat space is the geometry you learned in school. Euclidean, clean, the universe as a perfect grid. And like negative curvature, a flat universe has no edge. It goes on forever. For most of the 20th century, physicists had no clean way to measure which of these three descriptions fit the universe we actually live in. The math allowed all three. Then, starting in the late 1980s, something changed. Instruments got sensitive enough to read the cosmic microwave background in real detail, and the CMB turned out to be carrying the answer. Here is how the measurement works. The CMB has tiny temperature fluctuations, patches that are slightly warmer or slightly cooler than average. Those patches have a characteristic size set by physics in the very early universe. Physicists can calculate from first principles how large those patches should appear in the sky. But how large they appear to us depends on the curvature of the space the light has traveled through. If space is positively curved, the patches look bigger than they should. If space is negatively curved, they look smaller. If space is flat, they look exactly the size the equations predict. In the early 1990s, experiments began measuring those patch sizes. By the late 1990s, two balloon-borne observatories, one called Boomerang and one called Maxima, gathered enough data to give a real answer. The patches were the right size. Space was flat, not approximately flat, not flat within a generous margin, flat to the precision limit of the instruments. Later missions, including the WMAP satellite and then the Planck satellite, pushed that measurement further. Same answer, flat. This is the kind of result that looks simple and is actually devastating in its implications. Because a perfectly flat universe cannot be finite. The geometry will not allow it. On a sphere, curvature closes the space back on itself. That is what allows the sphere to be finite without having a boundary. Take that curvature away, and the mechanism that closes the space is gone. There is nothing to bring you home. You walk in one direction forever, and forever is what you get. Some physicists push back here and point out that a flat universe could still be finite if it has a strange, non-trivial topology, a shape that wraps back on itself the way the surface of a donut does, even without any detectable curvature. That is technically true. Scientists have actually looked for signatures of this in the CMB, searching for repeated patterns that would appear if the universe looped back. Nothing has turned up. The universe, as far as any measurement has ever reached, shows no sign of wrapping around. It just goes. So what does flatness actually mean for the question this whole series is circling? It means the most natural reading of what we measure is a universe that extends infinitely in all directions. Not very large, not almost infinite, infinite. Every direction you could choose, space continues without end. The observable universe, that 46 billion light-year sphere centered on wherever you happen to be standing, is not the universe. It is a region of the universe, a region bounded not by any wall or physical limit, but by the amount of time light has had to travel since the Big Bang. Past that boundary, by everything the geometry is telling us, space keeps going. There is something almost deliberately understated about the way this result got announced. A pair of balloon experiments in Antarctica and a handful of collaborating physicists produced measurements of temperature fluctuations in ancient light and concluded, from the angles of those fluctuations, that the universe is probably infinite. The headlines moved on quickly. The implications did not move on. They are still sitting there, enormous and mostly unexamined, every time someone looks up at a night sky and wonders what's out there past the edge of everything we can see. The geometry says there is no edge. It says the space you cannot observe continues the same way the space you can observe does, with nothing to stop it. The data does not confirm a wall. The data does not confirm a boundary. A perfectly flat universe, infinite in all directions, with no curvature to ever bring you home. That is what the data says we live in. Galaxies are not sitting still in space waiting for their light to reach us. They are moving, and the movement is not slowing down. In the early 1920s, an astronomer named Edwin Hubble was measuring the distances to faint smudges of light scattered across the sky. Most people assumed those smudges were clouds of gas inside our own galaxy. Hubble proved they were entire separate galaxies, each containing hundreds of billions of stars, sitting at distances so enormous that the numbers barely meant anything. That discovery alone would have made him one of the most important scientists who ever lived. But then he noticed something stranger. Every single one of those galaxies, in every direction he looked, was moving away from us. Not just a few of them, not most of them, all of them. The immediate instinct is to assume this means we are at the center of some giant explosion, everything fleeing outward from a single point where we happen to be standing. That is the wrong picture. The right picture is harder to build in your head, but it is worth the effort. Imagine a loaf of raisin bread rising in an oven. Every raisin moves away from every other raisin as the dough expands. No raisin is at the center. No raisin is special. From any single raisin, all the others appear to be retreating. The galaxies are the raisins. Space itself is the dough. This is not a metaphor that breaks down at the edges. It is actually how the physics works. The galaxies are not traveling through space away from us. The space between us and them is stretching. The distinction sounds like wordplay, but it has a consequence that stops most people cold when they first hear it. Because it is space itself expanding rather than objects moving through space, the recession speed of a distant galaxy is not limited by the speed of light. Objects cannot move through space faster than light. But space has no such speed limit. Space can stretch as fast as it wants. And at large enough distances, it stretches fast enough that galaxies are moving away from us faster than light could ever travel. There are galaxies we can see right now that are already receding from us at twice the speed of light. This is not a violation of any law of physics. It is a consequence of one. And it has a deeply strange implication that takes a moment to fully settle in. In the 1990s, two independent teams of astronomers were trying to measure how quickly the expansion of the universe was slowing down. Everyone assumed it was slowing down. Gravity pulls things together. The Big Bang had sent everything flying outward, and gravity should have been gradually putting the brakes on. The two teams were simply trying to measure how hard those brakes were applied. They used a particular type of exploding star as a measuring tool, a type of supernova that always explodes with the same intrinsic brightness, making it possible to calculate exact distances across billions of light years. When the results came back, both teams found the same answer. The expansion was not slowing down, it was speeding up. The universe was not coasting to a gradual stop, it was accelerating. The discovery earned the Nobel Prize in Physics in 2011, and it introduced a concept that physicists still cannot fully explain: dark energy, the name given to whatever force is driving the acceleration. What this acceleration means for the edge of everything is the part that deserves your attention. When Hubble first mapped those retreating galaxies, the situation was uncomfortable, but not hopeless. A sufficiently patient civilization might eventually reach distant galaxies if the expansion was slowing. With an accelerating expansion, that option closes permanently. The farther away a galaxy is, the faster it recedes. Push that logic out far enough, and you reach galaxies so distant that the space between us and them is expanding faster than light. Any photon those galaxies emit today, aimed directly at us, will spend its entire existence swimming upstream against a current of expanding space that is simply too strong. The photon will never arrive, not in a billion years, not ever. Here is where it gets genuinely strange. Some of the galaxies currently visible in our sky, galaxies whose ancient light is reaching our telescopes right now, have already crossed that threshold. The light arriving tonight left those galaxies billions of years ago, when they were close enough that their light could still make the journey. Since then, the expansion has carried those same galaxies so far away that any new light they emit today will never reach us. We are receiving the last message they will ever send us, and we do not know it is the last one. The channel is open while we watch, and it will simply go dark, not with a dramatic cutoff, but with a gradual fade as the most distant signals get stretched by expansion into wavelengths too long to carry usable information. This is the acceleration's sharpest edge. A universe expanding at a constant rate would be strange enough. A universe expanding at an increasing rate is one that is actively, continuously, and permanently reducing the amount of itself that any observer will ever be able to interact with. Right now, the observable universe contains roughly 2 trillion galaxies. Over cosmic time, as the acceleration continues and more galaxies cross the event horizon, the number accessible to any future civilization here will fall. The galaxies of the local group, the Milky Way, Andromeda, and a handful of smaller companions, are gravitationally bound tightly enough that expansion will not pull them apart. Everything beyond that group is, on a long enough timeline, leaving for good. The universe is not just large, it is not just expanding, it is running from itself, pulling its own far reaches permanently out of reach of any observer sitting anywhere within it, including here, including now. Every second, the universe is putting more of itself permanently beyond our reach, and nobody knows when or whether that process ever stops. Astronomers draw two different circles around the observable universe, and understanding why they are different circles is one of the stranger exercises in modern cosmology. The first circle is called the particle horizon. It marks the farthest distance from which light has had time to reach us since the Big Bang, 13.8 billion years ago. That sounds simple enough. Light travels at a fixed speed. The universe has a fixed age, so there is a fixed distance beyond which no signal has had time to arrive. The particle horizon sits at roughly 46 billion light-years in every direction, and everything inside it is, at least in principle, observable. That is the circle most people picture when they imagine the edge of the universe. It is the lit room. It is the boundary of the known. The second circle is stranger. It is called the cosmic event horizon, and it does not describe what we can see now. It describes what we will ever be able to see, given infinite time. Those two things sound like they should be the same. They are not, and the reason they are not is the same thing covered in the previous section. The expansion of the universe is accelerating, because space is not just expanding, but expanding faster and faster. There is a distance beyond which any light emitted today will never reach us. The space between here and there will stretch too quickly. The signal will run and never close the gap. That boundary is the cosmic event horizon, and it sits at a much closer distance than the particle horizon, roughly 16 billion light-years, not 46. Sit with that for a moment. The particle horizon tells you about a sphere 46 billion light-years across. The event horizon closes off everything beyond about 16 billion light-years permanently. Anything sitting in the gap between those two circles, and that gap contains an enormous amount of universe, is technically visible right now because old light from it has already reached us. But new light from those regions, emitted today, will never arrive. Those galaxies are already gone in a meaningful sense. We can see their past. We will never see their future. This is not an abstraction. Astronomers have identified thousands of galaxies currently sitting inside our particle horizon, but outside our event horizon. We are watching them right now. Hubble and its successors have photographed them. They are real, mapped, and catalogued. What those photographs show is ancient light. Those galaxies, as they were billions of years ago, when the universe was young enough that the light could still make the crossing. The galaxies themselves are still out there, still evolving, still exploding and merging and forming new stars. None of that will ever reach us. The connection is severed. The line went dead, and we did not notice because the last message took so long to arrive. Now here is where it gets genuinely unsettling. Because expansion is accelerating, even galaxies currently inside our event horizon will eventually cross it. Over time, as dark energy continues pushing space apart at an increasing rate, galaxies that are visible today will drift across that 16 billion light-year boundary. Their light will stretch. Wavelengths will redshift from visible to infrared, to radio waves to wavelengths so long they carry almost no energy. then nothing. The signal does not stop sharply. It fades over cosmic timescales into silence. But the endpoint is the same. Those galaxies will go dark to us, not because they stopped shining, but because the space between us and them will eventually be expanding too fast for any light to bridge. This means the observable universe, in a specific and important sense, is shrinking. The particle horizon keeps growing. Light from farther regions keeps arriving, slowly expanding our view. But the event horizon is drawing inward, cutting off more and more of the cosmos from any future communication. In the very far future, tens of billions of years from now, the galaxies beyond our local group will have redshifted into complete unobservability. Astronomers living in that era, if any exist, will look out at a night sky and see almost nothing, not because the universe emptied out, because they are sealed inside a shrinking bubble of visibility, surrounded by a cosmos they have no instrument to detect and no way to reach. The parallel to a black hole's event horizon is not casual. It is exact in a structural sense. An event horizon around a black hole marks the point past which nothing, no matter, no light, no signal of any kind, can escape outward. Cross it going the wrong direction, and information about the outside world is permanently lost to you. The cosmic event horizon works the same way in reverse. Cross it going outward, and your signals never come back. Sit on this side of it, and no signal from the other side will ever arrive. The physics is different in its details. The consequence is identical. You are on one side of a one-way barrier, and the universe enforces that barrier without exception. There is no engineering solution to this. No telescope built in any future century will see past the event horizon. A civilization 1 trillion years more advanced than ours would face the same wall. The barrier is not about sensitivity or resolution or funding. It is written into the geometry of accelerating space. Information requires a carrier. Every carrier travels at or below the speed of light. If the space between 2 points expands faster than light can cross it, no carrier gets through. The math closes the door and removes the handle. Beyond the event horizon, information about what exists there is not merely hard to get. It is gone, permanently and by law. The most conservative, least dramatic answer to what lies past the edge of the observable universe is also, in its own way, the most unsettling one. No exotic physics, no parallel dimensions, no fire and collapse. Just more of this. Galaxies, filaments of matter, vast, empty voids, and the same rules running quietly in all of it. The region just past your cosmic horizon almost certainly looks like the region just inside it. Clusters of galaxies pulling on each other. Supernovae going off in slow motion. Stars burning through hydrogen at the same rate they burn through it here. The universe just continuing, as if the boundary you cannot see past means nothing. Because to the universe, it doesn't. This idea has a name. Astronomers call it the cosmological principle, and it is one of the foundational assumptions of modern science. The principle says that on large enough scales, the universe looks the same in every direction and from every location. Not identical in detail, your neighborhood looks different from mine, but statistically uniform. Smooth the map out far enough and no region outweighs any other. No center, no edge, no special spot. When you look at galaxy surveys, the largest maps humanity has ever assembled, this is what you find. Zoom out far enough, and the lumpy web of matter flattens into something almost perfectly even. The cosmological principle is not an article of faith. It is a reading of the data, and the CMB backs it up in the strongest possible terms. That ancient radiation, coming from every direction in the sky, is uniform to better than 1 part in 100,000. Wherever you look, the early universe had the same temperature, the same density, the same character. The differences are there, tiny ripples that would eventually grow into galaxies. But the baseline is the same everywhere we can check. Every direction we can probe points to a universe that was already statistically uniform before the first star ignited. If the universe was uniform inside the horizon in every direction, the most natural conclusion is that it was uniform outside it too. Not guaranteed, but natural. So what does that mean for the region just past the edge of what you can see? It means there are probably galaxies out there, galaxy clusters, filaments hundreds of millions of light years long, threaded through with dark matter, lined with glowing points that are suns you will never see. It means there are almost certainly planets, dust clouds cooling into new solar systems, dying stars expanding into red giants and then going dark. The whole machinery of the universe running on the same physics, in the same patterns, past a horizon that is entirely invisible to you and entirely irrelevant to what happens on the other side of it. Here is where things get genuinely strange. If space is infinite, and the geometry we measured strongly suggests it is, then the amount of matter past your horizon is not just large, it is infinite. Infinite matter governed by a finite set of physical laws, distributed at roughly the same density as the observable universe, arranging itself into every configuration those laws permit. And that is where the unsettling part begins. There are only so many ways to arrange matter. Atoms can only be stacked in so many configurations. A region of space containing roughly the same number of particles as your observable universe has an enormous but finite number of possible arrangements. Think of it like a very long string of coin flips. Heads and tails can only combine in so many distinct sequences before they start to repeat. With an infinite number of coin flips, every finite sequence must occur, not once, but infinitely often. The same logic applies to space. In an infinite universe with the same density of matter as ours, every possible arrangement of particles repeats, including the arrangement that produced our solar system, including the arrangement that produced Earth, including the arrangement that produced you, reading this, in this moment, with exactly this particular configuration of memories and neurons and uncertainty about where the universe ends. Physicists have actually tried to put a number on how far away the nearest copy of your observable universe would statistically be. The estimate that shows up most often is staggering. The nearest region of space with a matter configuration essentially identical to our entire observable universe would be expected to sit somewhere around 10 to the power of 10 to the power of 118 meters away. Write that out, and you would fill more paper than exists. It is not a number that connects to any human intuition, but the logic behind it is straightforward. Finite number of configurations, infinite space. Repetition is not just possible, it is mandatory. What that means in practice is harder to absorb. Somewhere past the horizon, with enough distance, there is a planet that formed the same way Earth did. Oceans, continents, life that evolved under a familiar sun. And if you follow that reasoning far enough, somewhere there is a version of this exact moment playing out, with all the same particles in all the same positions, right down to the particular thought you are having right now. The physics does not forbid it. In an infinite flat universe, it demands it. This is not a claim about souls or identity, or any philosophical question about what makes you you. It is a claim about matter, about the finite number of ways things can be arranged, about what infinity actually forces on a universe that takes it seriously. The copy of you that exists past the cosmic horizon is not you in any meaningful sense. It is just an arrangement of atoms that matches yours. But that matching is not a coincidence or a miracle. It is arithmetic. Infinite space with the same rules and the same matter density as ours does not just allow for repeated structures, it mathematically requires them. There is a word that physicists use with extraordinary casualness, given what it actually means. Infinite. Not very large. Not larger than we can measure. Not so big that the difference stops mattering. Infinite. Without end. A thing that goes on not for a long time, but forever. Not across a great distance, but across every distance. Without stopping, without thinning, without approaching anything you could call a boundary. When a physicist writes that word in an equation, it slides past almost without comment. When you actually try to hold what it means as a physical claim about real space, something in the mind quietly refuses to cooperate. That resistance is worth taking seriously. Human intuition was built for a world of plains and hills and horizons, for distances you can walk and volumes you can fill. Infinity is not an experience. It is a conclusion, and the path to that conclusion runs through some of the more disorienting territory in modern cosmology. To understand what exists past the final edge of the observable universe, you have to first sit with the genuinely strange possibility that space has no final edge at all, not because we haven't reached it yet, but because there is nothing to reach. Here is a way to picture what is being claimed. Imagine you are standing on an enormous flat plain. Fog sits at the horizon in every direction, maybe a mile out, maybe 2. You can see clearly inside that circle. Beyond it, nothing. Now the fog is not a wall. The plain does not stop where your vision does. If you walk toward the fog, you would pass through it and find more plain, stretching out ahead. The fog follows you. Your circle of visibility travels with you wherever you go, and the plain keeps going. That is roughly the situation with the observable universe. The horizon is the fog. The 46 billion light-year sphere is the circle you can see clearly. And the question is whether the plane ever ends. The measurements say it probably does not. When satellites mapped the cosmic microwave background with enough precision to detect its geometry, what they found was a universe that is spatially flat to the limits of what any instrument could resolve. Flat geometry is significant. A positively curved space, like the surface of a sphere, is finite. Walk far enough in one direction and you come back to where you started. A flat space has no such trick. Parallel lines stay parallel forever. Triangles always add up to 180 degrees. There is no curvature pulling you gently back toward home. If space is genuinely flat, it extends outward without limit in every direction, and the observable universe sits inside it, the way a single grain of sand sits inside a desert with no border. That comparison is not poetic exaggeration. It may actually undersell the situation. The observable universe is 46 billion light-years in radius. That sounds enormous because by every human standard it is. But if space is infinite, then the ratio of the observable universe to all of space is not a small number. it is zero. Mathematically, any finite region divided by infinity is zero. The 46 billion light-years we can see is not even a rounding error. It is nothing in the strictest sense of the proportion. Physicists who work on this tend not to dwell on that fact, probably because there is nothing useful to do with it, but it deserves to be said plainly. Not everyone is convinced that actual physical infinity is real rather than a symptom of incomplete models. This is a legitimate debate. Some physicists argue that infinity appearing in an equation is usually a sign that the equation has broken down, that you have pushed a good model past where it applies. On this view, a truly infinite universe is not a discovery, but a placeholder, something the math produces when we don't yet know enough to constrain the answer properly. The concern is reasonable. Physics has a history of infinities that turned out to be problems to be solved, not features of reality. Whether cosmic spatial infinity falls into that category is genuinely unresolved. What nearly everyone does agree on is this: even if space is finite, it is almost certainly far larger than the 93 billion light-year bubble we can observe. The CMB measurements constrain the overall curvature of space tightly enough that if space does curve back on itself, the full circumference of that curve must be enormously larger than our observable sphere. Some estimates put the lower bound at hundreds of times larger. Others put it much higher. The observable universe being a small fraction of total space is not a fringe position, it is the mainstream one. So when someone says the universe is 93 billion light-years across, what they mean, with appropriate honesty, is that the observable universe is 93 billion light-years across. The two phrases are not the same thing, and treating them as equivalent is an error so common it has stopped feeling like one. The observable universe is the part with a postcode. It is the part the laws of physics allow us to examine. Total space, the actual universe, sits outside those laws in the sense that we cannot reach it, cannot measure it, cannot probe it with any instrument currently imaginable. And here is the thing that should make this feel strange rather than comfortable. Every time you have heard someone describe the scale of the cosmos, every time a documentary has walked you through the hierarchy from Earth to solar system, to galaxy, to local group, to the observable universe, the story has been stopping at the fog. The plane keeps going. The fog is just where we lose the light. When astronomers talk about the universe as if it were the same thing as the observable universe, they are making an assumption so enormous it barely registers, and it is almost certainly wrong. To understand what might exist past the final edge of everything we know, you have to go back to a moment that happened before anything we can observe. A moment in the first 10 to the minus 36 seconds of existence. That number is not a typo. It is a fraction so small that writing it out in decimal form would require you to place 35 zeros between the decimal point and the first significant digit. Nothing in human experience scales down to that. Nothing in biology, nothing in chemistry, nothing in ordinary physics gives you any intuition for a unit of time that small. But something happened in that window, and what happened there shaped everything that came after, including the size of the observable universe, the flatness of space, and the question of whether our Big Bang was unique. The theory is called cosmic inflation. It was first proposed by physicist Alan Guth in 1980, and the core idea is almost violent in its simplicity. In that first unimaginably brief window, the universe did not expand at the pace we observe today. It expanded exponentially. Not fast, exponentially. The difference matters. Fast growth adds. Exponential growth multiplies over and over in vanishingly small increments of time. A region of space far smaller than a single proton ballooned to roughly the size of a grapefruit in something like 10 to the minus 32 seconds. That sounds small. It is not. In terms of the factor by which space itself stretched, inflation expanded the universe by a number that dwarfs anything else in cosmology. The universe you can see tonight, stretching 46 billion light-years in every direction, traces back to a patch of space during inflation that was smaller than an atom. So why do physicists take this seriously? Because inflation solves two problems that had no other clean solution. The first is called the horizon problem. Look in opposite directions in the sky, as far as any telescope can reach, and the temperature of the universe in both directions is identical to a precision of 1 part in 100,000. Those two regions of sky are so far apart that, at the expansion rate we observe today, they could never have been in contact with each other. They had no time to exchange heat, no time to equilibrate. They should not look the same. They do. Inflation explains this by pointing out that before the expansion, those regions were packed together, close enough to reach thermal equilibrium, and then inflation stretched them to opposite ends of the observable universe in a fraction of a second. The sameness is not a coincidence, it is a memory. The second problem is flatness. Space is geometrically flat, measured to extraordinary precision by instruments studying the cosmic microwave background. A universe that starts out with even a tiny curvature should, over 13.8 billion years of expansion, have that curvature amplified dramatically. The fact that space is still flat means it started almost perfectly flat, which seems like an extraordinary coincidence unless inflation is true. Inflation naturally drives any initial curvature towards zero. Whatever shape the universe had before inflation, the exponential expansion would have stretched it so violently that any curvature would be smoothed away, the same way a small wrinkle on a balloon disappears as you inflate it. Inflation doesn't just explain flatness, it predicts it. Here is where things get stranger. Inflation requires a field, physicists call it the inflaton field, to drive the expansion. Think of it as a kind of energy stored in space itself, pushing outward with enormous pressure. For inflation to end, this field has to decay. It has to release its energy and convert it into the hot, dense soup of particles that became everything we can observe. That transition, the moment inflation ends and the fireball begins, is what we call the Big Bang. The heat, the light, the matter, all of it comes from the inflaton field, finally letting go. But here is the question that changes everything. What if that field does not let go everywhere at once? Quantum mechanics, the physics of the very small, introduces uncertainty into every process at the fundamental level. The inflaton field is a quantum field. It fluctuates. In some regions of space, those fluctuations push the field down toward decay, and inflation ends. In other regions, the fluctuations push the field back up, and inflation keeps going. The regions where inflation ends become fireballs, big bangs, expanding universes. The regions where inflation continues just keep expanding, faster than anything inside them can escape. And here is the key. The inflating regions expand so fast that they always outpace the regions where inflation stops. No matter how many pockets collapse, see into big bangs, The background of still inflating space always grows faster. Inflation, once started, never fully ends. This is what physicists call eternal inflation. Our entire observable universe, every galaxy, every star, every atom of everything that has ever existed within the 46 billion light-year sphere we have spent this series mapping, is one of those pockets. One small region where the inflaton field happened to decay. The fireball that resulted was our Big Bang. Everything you have ever seen, touched, or measured came from that single event of inflation, ending in one particular patch of an eternally expanding background space. That background is still out there. It is still expanding. Other pockets are still forming, collapsing into their own fireballs, producing their own Big Bangs, right now, in a region of space so far beyond our cosmic horizon that no signal from there will ever reach us. Were we special? Was our Big Bang the one that mattered? Eternal inflation gives a quiet, almost unsettling answer. There is nothing in the theory to suggest our pocket is different from any other. The same physics that produced our universe is producing others, constantly, in a background that has no edge and no clock. The question of what came before the Big Bang stops being unanswerable and starts being almost mundane. What came before was more inflation, and before that, more inflation, stretching back without a starting point in any direction. If eternal inflation is correct, our Big Bang was not the beginning of everything. It was one spark in a fire that has no beginning and no end. Were we observing a star's final moments as they unfolded? That was the question in 2019. Throughout history, astronomers have sought to understand the ultimate fates of stars. The observation of stellar death represents one of the most compelling frontiers in astrophysical research. When a massive star approaches the end of its life cycle, it undergoes dramatic transformations that can be detected from Earth using modern astronomical instruments. These final stages involve violent processes that reshape the star's structure and release enormous amounts of energy into space. In 2019, the astronomical community was particularly focused on several celestial objects that exhibited unusual behavior. Advanced telescopes equipped with sophisticated detection systems allowed researchers to monitor stars in unprecedented detail. The question of whether we were witnessing a star's death in real time captured the imagination of scientists and the public alike. This inquiry reflected humanity's deep curiosity about the cosmos and our place within it. Stars spend most of their lives in a relatively stable state, converting hydrogen into helium through nuclear fusion in their cores. This equilibrium can persist for billions of years, depending on the star's mass. However, once a star exhausts its nuclear fuel, its fate is sealed by the laws of physics. The more massive the star, the more violent and spectacular its final explosion tends to be. These cosmic fireworks represent some of the most energetic events in the universe. The year 2019 was significant for several reasons in stellar astronomy. Multiple observatories were trained on candidate objects that showed signs of imminent stellar death. Researchers analyzed data from radio telescopes, optical instruments, infrared detectors, and X-ray satellites. This multi-wavelength approach provided a comprehensive picture of what was happening in these distant stellar systems. The coordination between different observing facilities represented the modern state of collaborative astronomical research. One particularly intriguing case involved the behavior of a red supergiant star that had been acting unexpectedly. Red supergiants are evolved massive stars that have expanded enormously and are approaching the end of their lives. When such stars undergo sudden changes in brightness or emission patterns, astronomers take notice. The possibility that we might be witnessing the final years or even months before a catastrophic explosion excited the astronomical community. Predicting the exact moment of a star's death remains extraordinarily difficult. Stars can exhibit erratic behavior in their final stages, with sudden increases or decreases in luminosity. They can undergo dramatic changes in their chemical composition as nuclear fusion reactions accelerate. The complexity of stellar physics means that even with our best models and observations, surprises still occur. This unpredictability is part of what makes stellar astronomy so fascinating and challenging. The mechanisms behind stellar death vary depending on the star's mass and composition. Low-mass stars like our Sun will eventually shed their outer layers and leave behind a white dwarf. Intermediate mass stars might produce planetary nebulae, beautiful structures of expelled gas illuminated by the dying star's remaining core. High-mass stars, however, face a more violent end. When a massive star runs out of fuel, its core can no longer support itself against the crushing force of gravity. The collapse of a massive star's core can happen with shocking rapidity. Within hours or even minutes, the iron core implodes catastrophically. This collapse rebounds in a shockwave that tears the star apart in a supernova explosion. A single supernova can briefly outshine an entire galaxy containing billions of stars. The energy released is almost incomprehensible to the human mind. In 2019, several candidate objects were under intense scrutiny by the astronomical community. Researchers had identified stars that showed characteristics suggesting they were in the late stages of stellar evolution. Regular observations tracked any changes in these stars' properties. Teams of scientists around the world coordinated their efforts to ensure continuous monitoring. The possibility of catching a supernova in the act of occurring drove this collaborative effort. Supernovae are rare events when observed from our perspective on Earth. In a typical large galaxy, a supernova occurs only once every 100 years or so. This rarity makes each potential supernova sighting scientifically valuable. Catching a supernova early in its explosion, before it reaches peak brightness, is especially important. Early observations provide crucial information about the explosion mechanism and the star's composition. The question posed in 2019 reflected both excitement and uncertainty. Astronomers had strong suspicions about certain objects, but could not be entirely certain of what would happen next. Science progresses through careful observation, analysis, and comparison with theoretical models. The 2019 observations contributed to our understanding of stellar evolution, regardless of whether a supernova occurred during that specific year. Each data point adds to humanity's collective knowledge of the universe. Technology has greatly enhanced our ability to detect and study distant stars. Modern spectrographs can analyze the light from stars and reveal their chemical composition. Photometric instruments can measure brightness changes with extreme precision. Infrared observations pierce through dust that blocks visible light. X-ray and ultraviolet observations reveal the hottest regions around dying stars. This technological toolkit allows astronomers to ask increasingly sophisticated questions about stellar physics. The 2019 investigations demonstrated the maturity of modern observational astronomy. Multiple teams competing and cooperating simultaneously brought rigor to the investigation. Peer review ensured that observations and interpretations met scientific standards. The data was made available to the broader scientific community for analysis and reanalysis. This open approach to science accelerates discovery and validates findings. Whether we were truly witnessing a star's final moments in 2019 remained an open question that would be answered only by time and continued observation. The search itself represented humanity's ongoing quest to understand the cosmos. String theory, the most ambitious attempt to unify all of physics into a single framework, has a problem that turned out to be either its greatest flaw or its most important prediction, depending on who you ask. The theory started as an attempt to do something that has defeated physicists for a century. Every other force in nature has been brought under a single mathematical roof except gravity. Quantum mechanics describes the very small with extraordinary precision. General relativity describes the very large with equal precision. When you try to make them talk to each other, the math breaks down. String theory proposed a way out. Instead of treating the fundamental constituents of reality as point particles, it treats them as tiny vibrating strings of energy. Different vibrational modes of the same string produce different particles. One vibration gives you an electron, another gives you a photon. A particular mode gives you the particle that carries gravity. On paper, this is elegant. In practice, it came with a condition nobody asked for. The equations only work if space has more than 3 dimensions. Not 4, not 5, 10, or 11, depending on the version. Which means that if string theory is correct, there are 6 or 7 spatial dimensions that you have never experienced and never will. Physicists call this an inconvenience. What it actually is, once you follow the implications out far enough, is a door into something almost too large to think about. Those extra dimensions have to go somewhere. They cannot just sit alongside the 3 we experience without being detectable. So the theory requires them to be compactified, which means curled up into shapes so small that no instrument we have or could build would ever resolve them. Think of a garden hose seen from a distance. It looks like a line, a one-dimensional object. Get close enough and it has thickness, curvature, a second dimension wrapped around the first. The extra dimensions of string theory work the same way. They are there. They are just small enough to be invisible. Here is where the problem enters. There is not one way to compactify 6 extra dimensions. There are many. The extra dimensions can be curled up into an enormous variety of geometric shapes, each with different topologies, different sizes, different configurations. Each distinct configuration produces a universe with different physical constants, a different value for the strength of gravity, a different mass for the electron, a different cosmological constant, a different everything. The number of geometrically distinct ways to compactify the extra dimensions has been estimated at roughly 10 to the power of 500. Not 10 to the 5th, 10 to the 500th. This is called the string landscape. Each point on that landscape is a possible set of physical laws, a possible universe. For a long time, physicists treated this as an embarrassment. A good theory of everything should predict one universe, the one we live in. A theory that produces 10 to the 500 equally valid universes looks less like a theory and more like a shrug. Some physicists still feel that way. Others began to suspect the landscape wasn't a flaw. It was the answer to a question they had been asking for decades. That question connects directly to what the last section left you with. If eternal inflation is correct, new bubble universes are constantly forming as pockets of the inflating background space collapse into their own big bangs. The question was always what physics each of those bubbles gets. If the string landscape is real, the answer might be that each bubble lands on a different point in the landscape. Each bubble draws a different compactification of the extra dimensions, like pulling a different card from an incomprehensibly large deck. Each bubble gets different constants, different particle masses, a different cosmological constant, different rules. The inflating background space keeps producing bubbles. Each bubble is a universe. Each universe runs a different experiment in physics. Some of those experiments produce constants that allow atoms to form. Some don't. Some produce stars. Some produce nothing but diffuse hydrogen that never clumps. Some produce a cosmological constant so large that space tears itself apart before a single galaxy can condense. Most of the landscape, by most estimates, produces something hostile to complexity. A small fraction does not. This is where the reasoning gets circular in a way that either satisfies you or unsettles you, depending on your disposition. The question of why our universe has the constants it has, why gravity is exactly the strength it is, why the cosmological constant is not 1 billion times larger, has no clean answer inside a single universe picture. The numbers look finely tuned, suspiciously so. In a landscape picture, the question changes shape. You stop asking why the constants are what they are, and start asking which universes in the landscape produce observers capable of noticing. The answer is the ones with constants in the right range. We are in one of those because we could not be in any other. This is the anthropic principle, and it is either a profound insight or a way of explaining ever, a thing by explaining nothing, and physicists have been arguing about which of those it is since the 1980s. What nobody disputes is the scale. If the string landscape exists, the catalogue of possible universes is not a short list. It is not even a long list. Each configuration is geometrically distinct. Each produces a coherent set of physical laws. Each could, in principle, correspond to a bubble universe somewhere in the eternally inflating background. 10 to the 500 is a number so large that describing it as astronomical would be an insult to astronomy. And if string theory is right, every single entry in that catalogue is a real place. The universe appears to have been built with extraordinarily precise specifications, and explaining why those specifications are what they are turns out to be one of the hardest problems in all of science. The string landscape gives you 10 to the 500 possible universes, each with different physical constants. That number only matters if the constants actually make a difference, and they do. They make a difference so large, so decisive, that physicists have spent decades trying to figure out whether the values we measure are accidental, inevitable, or something else entirely. Start with gravity. The gravitational constant, the number that sets how strongly mass pulls on other mass, is extraordinarily weak compared to the other fundamental forces. It is roughly 10 to the 36 times weaker than electromagnetism. That sounds like a flaw. It is not. If gravity were even modestly stronger, stars would form, burn hot, and collapse in millions of years instead of billions. Life needs time, billions of years of it. A universe with slightly stronger gravity is a universe that never gets around to biology. The window for the gravitational constant to land in a range that permits complexity is narrow, and we are sitting squarely inside it. Then there is the cosmological constant. This is the number that describes the energy density of empty space, the quantity tied directly to dark energy, and the expansion rate of the universe. It is almost zero. Theoretical calculations of what it should be, based on quantum field theory, suggest a value roughly 10 to the 120 times larger than what we actually measure. That is not a small discrepancy. That is the largest mismatch between theory and observation in the history of physics. And here is what makes it strange. If the cosmological constant were even a fraction of what the equations naively predict, space would have expanded so violently in the early universe that matter never had the chance to clump together. No galaxies, no stars, no periodic table worth mentioning. The cosmology Cal constant appears to have been dialed down to almost nothing, with a precision that has no physical explanation anyone can fully account for. The proton-neutron mass difference is another one. A proton is slightly lighter than a neutron, by about 0.1%. That tiny gap matters enormously. If the neutron were lighter than the proton instead of heavier, free protons would decay into neutrons. Hydrogen would be unstable, and the chemistry that underlies all known life simply would not exist. Change that mass difference by a small fraction in either direction, and the periodic table either collapses or never assembles properly in the first place. The number has to land in a very specific range, and it does. You can keep going. The strong nuclear force, which holds atomic nuclei together, is precisely tuned to allow carbon to form inside stars. Carbon is the backbone of organic chemistry. If that force were a few percent weaker, carbon nuclei would not be stable. A few percent stronger, and hydrogen would fuse so readily in the early universe that it would all burn off before stars could sustain themselves. Fred Hoyle, the British astronomer, predicted an energy resonance in carbon nuclei before it was discovered, specifically because he reasoned that carbon had to be able to form in stellar interiors, and the only way that was possible was if such a resonance existed. He was right. The universe builds carbon, and the numbers are set just right to allow it. So what do you do with this? There are two broad answers, and neither is comfortable. The first is that the constants are what they are by design, that some intelligence, some agency outside the physical framework, selected these values. This is an old answer, and it feels like an answer to many people. But it is not a scientific answer. It does not generate predictions you can test. It does not point toward any new physics. Science can acknowledge the question without being able to touch it, and this particular explanation lives permanently outside the boundaries of what experiments can reach. The second answer is the multiverse. If there are enough universes, with enough variation in their physical constants, then some fraction of them will land on values that allow complexity. Observers, by definition, can only find themselves inside universes where observers are possible. This is the anthropic principle. It sounds almost trivial when you state it plainly. Of course, we are in a universe compatible with our existence. Where else would we be? But the logic has real teeth. It means you do not need to explain why the constants are finely tuned. You only need enough universes with enough variation, and selection takes care of the rest. The string landscape, with its 10 to the 500 vacua, provides exactly that kind of variation. Eternal inflation provides the mechanism to populate the M. Put the two together and the fine-tuning problem dissolves, not because the numbers were chosen carefully, but because every combination was tried somewhere. The problem is that this explanation is almost impossible to test. You cannot reach the other universes. You cannot observe the ensemble. You are making an inference about an infinite population from a sample size of 1. Some physicists find this deeply unsatisfying. A theory that explains everything by appealing to an unobservable infinity of cases, they argue, is not really explaining anything. Others think the logic is sound, and that demanding a testable mechanism for every inference is an overcorrection. The debate has not been settled. It is not close to being settled. What is settled is the observation itself. The constants are narrow. The windows are real. The universe sits inside those windows with a precision that demands some kind of accounting. Either the numbers are what they are for a reason we do not understand, or the numbers are what they are because in the vast ocean of universes with different numbers, this is the one we happen to occupy. And nobody has yet found a way to determine which of those answers is true. There is a second kind of multiverse that has nothing to do with inflation or string theory, and it comes from the strangest corner of physics, the behavior of particles smaller than atoms. Everything covered so far, bubble universes, the string landscape, the fine-tuning of constants, all of that emerges from cosmology and high-energy physics, from questions about the large-scale structure of space. This multiverse is different. It grows out of a problem that physicists have been arguing about since the 1920s, and the problem sounds almost too simple to take seriously. When you measure a quantum particle, what actually happens? That question turns out to be genuinely unresolved. Here is the situation. Quantum mechanics describes particles not as objects with definite positions and speeds, but as waves of probability. An electron doesn't have a location the way a baseball does. It has a spread of possible locations, each with an associated likelihood. The math governing that spread is clean and precise. Physicists can calculate it exactly. The wave function, as it's called, evolves in a completely predictable way. Then something strange happens. The moment you measure the electron, the moment any detector interacts with it, the spread collapses. You don't get a cloud of probabilities. You get a single outcome. One position. One reading. The wave function, which had been spread across possibilities, snaps to a single answer. This is the measurement problem. The math before measurement is beautiful and deterministic. The act of measurement itself is neither. Nobody knows why observation selects one outcome. Nobody knows what does the selecting. For decades, the standard answer was to simply not ask. You plug in the wave function, you calculate the probability distribution, you compare your results to experiment, and everything matches perfectly. Don't worry about what's really happening underneath. This is what physicists call the Copenhagen interpretation, and for a long time, it was enough. Then, in 1957, a graduate student at Princeton named Hugh Everett proposed a different approach. What if the wave function never collapses? What if, instead of one outcome being chosen and the others disappearing, every outcome actually happens? The measuring device doesn't force the electron into a single position. The measuring device, along with the electron, along with the physicist doing the measuring, along with the entire universe, splits into separate branches, one for each possible outcome. In one branch, the electron landed here. In another branch, it landed there. Both are equally real. Neither knows about the other. This is the many worlds interpretation, and it solves the measurement problem completely. There is no collapse because there is nothing to collapse. The wave function always evolves deterministically. Every possibility plays out. The reason you only experience one outcome is that you are inside one branch. The other branches are just as real and just as convinced that their outcome was the one that happened. The implications are not subtle. Every quantum event that has more than one possible outcome generates a branching. Every radioactive atom that might or might not decay at a given moment. Every photon that might or might not be absorbed by a molecule. Every unstable particle at every moment in the history of the cosmos. The number of branchings that have occurred since the Big Bang is so far beyond astronomical that the word astronomical becomes useless. You are not just one version of yourself navigating one version of history. Under many worlds, every decision that had any quantum sensitivity, and most decisions do because neurons fire based on chemistry that depends on quantum processes, branches into separate histories. Somewhere in the structure, there is a version of you that made every choice differently. Physicists who take this seriously are not a fringe. A significant fraction of working physicists who think carefully about the foundations of quantum mechanics consider many worlds at minimum plausible, and some consider it the most coherent interpretation available. The reason is that it takes the mathematics of quantum mechanics at face value. It doesn't add any extra mechanism to explain collapse. It doesn't require any special role for observers or measurements. The wave function is real. It does what the equations say it does. Everything else follows. The cost is ontological extravagance, an incomprehensibly large number of parallel histories. But the equations don't charge extra for that. Now, here is where many worlds connects to everything else this script has been building. The inflationary multiverse produces separate regions of space with potentially different physical laws. The string landscape predicts an enormous number of possible universes with different constants. These are multiverses of space. Many worlds is a multiverse of history. They are completely independent ideas, arising from completely different areas of physics. If both are correct, you don't add them, you multiply them. Every bubble universe in the inflationary multiverse has been branching quantum mechanically since the moment it formed. Every entry in the string landscape catalogue of possible universes exists in every quantum branch it has ever generated. The already incomprehensible number of universes in eternal inflation gets raised to a power that has no name. And here is the piece that matters most for the question this whole series is asking. The region beyond your cosmic horizon, that vast unobservable expanse that has been the subject of every section before this one, has been quantum branching just as continuously as the corner you occupy. Every atom out there, every photon crossing some galaxy you will never see, every event in every star too far away to ever signal you, has been generating branches at the same rate as everything inside your observable sphere. The many worlds interpretation does not restrict its branching to the observable universe. The wave function of the universe is the wave function of the whole universe. If many worlds is right, there is not just one version of whatever exists past the cosmic horizon. There are infinitely many, branching every instant in ways that nobody can observe or verify. There is a version of cosmology that challenges something even more fundamental than the question of what lies past the edge. It challenges the idea that the Big Bang was the beginning. Every model we have looked at so far accepts one thing without arguing about it. There was a moment, roughly 13.8 billion years ago, when everything that exists exploded into being from an unimaginably hot, dense point. Eternal inflation puts that moment inside a larger framework. String theory fills in the physics around it. Many worlds branches off from it in every direction, but none of them seriously question whether it happened. The ekpyrotic model does, and it does so with math that a serious fraction of the physics community finds genuinely hard to dismiss. The original version of the idea came from a group of physicists working in the early 2000s. Their starting point was string theory's requirement that extra dimensions exist. In string theory, the 3 dimensions we move through are not all there is. There are additional spatial dimensions, and in some versions of the theory, our 3-dimensional universe is not floating in empty higher dimensional space alone. It sits on a membrane. Physicists call these objects brains, and the idea is that our entire observable universe, every galaxy, every star, everything, is the surface of one such membrane, drifting through a higher dimensional space called the bulk. Another brain could exist nearby. You would never see it. Nothing from it could reach you, because the particles and forces you are built from are locked to your membrane's surface. Only gravity leaks through. Here is where things get strange. The 2 brains are not stationary. They drift, and occasionally, over enormous stretches of time, they drift toward each other. When they collide, the energy released is catastrophic. From the perspective of anyone living on either membrane, it looks exactly like a Big Bang. Space floods with energy. Matter forms. The universe heats up and begins expanding. What we have always called the beginning of everything was, in this picture, just 2 membranes slapping together. The collision was not the start of time. It was an event inside a longer story. This was the ekpyrotic model, named after the ancient Greek word for conflagration. It had problems. The original version struggled to reproduce the specific pattern of temperature fluctuations we observe in the cosmic microwave background, the same fluctuations that inflation explains so cleanly. Physicists poked at it. Some of those problems got patched, others did not. The debate is still running, but the idea it seeded survived and grew into something broader. Cyclic cosmology takes the brain collision picture and extends it into a repeating sequence. The brains collide, triggering what looks like a Big Bang. The universe expands. Over hundreds of billions of years, the expansion slows, reverses, and the brains drift apart, pulled back toward each other by a force described through a scalar field threading the bulk. Then they collide again. Another Big Bang, another universe. The same brains, over and over, running through the same basic cycle, potentially without any starting point. No first collision, no original moment, just cycles, stretching back without limit. The newer versions of this idea, developed primarily by Paul Steinhardt and Neil Turok, moved away from the brain language and described the same physics through the evolution of a scalar field alone, which made the model somewhat cleaner and easier to work with mathematically. But the core implication stayed the same. Before our Big Bang was a previous universe, cooling and collapsing toward the conditions that triggered ours. Before that, another. each cycle lasting something in the range of 1,000,000,000,000 years before the bounce. What each previous cycle looked like is genuinely uncertain, and this is one of the harder questions the model has to answer. In some versions, almost no information survives the bounce. The extreme energies of the collision scramble everything. Each cycle starts fresh, with only the most basic physical constants inherited from the scalar field's properties. In other versions, subtle imprints of previous cycles might survive, encoded in the gravitational wave background, potentially detectable with sufficiently sensitive instruments. Nobody has found such a signal yet. The search is ongoing. There is a direct tension between cyclic models and eternal inflation, and it is worth being honest about. Eternal inflation is currently the more widely accepted framework, partly because it fits the CMB data more naturally, and partly because it has been developed in much greater mathematical detail over a longer period of time. Cyclic models are the challenger. Some physicists think they are on a dead end. Others think they are pointing at something real that the mainstream has been too quick to dismiss. The honest position is that neither model is proven. Both remain serious theoretical proposals. What cyclic cosmology does, regardless of which camp wins the argument, is force a specific and uncomfortable question. If the universe has been cycling forever, there is no creation event. There is no moment before which nothing existed. The question of what came before the Big Bang gets a clean, unsettling answer. Another universe, just like this one, running through the same sequence of expansion, cooling, and collapse. And before that, another. The phrase beginning of time loses its meaning entirely. This is a different kind of edge than the spatial horizon we have spent most of this series examining. It is not a boundary in any direction you could point. It is a boundary in time, or rather a challenge to whether time has a boundary at all. A universe that has always existed, cycling through an infinite series of expansions and collapses, carries its own kind of edge, not of space, but of time. And what exists past that edge is the same question asked in a different direction. Science has a hard problem with the question of what lies past the edge, and the problem is not that the answer is complicated. It is that the answer may be permanently inaccessible. Every theory covered so far, eternal inflation, bubble universes, the string landscape, cyclic cosmology, shares one uncomfortable feature. None of them can be tested in the traditional sense. You cannot send a probe beyond the cosmic event horizon. You cannot wait for a signal to arrive from a neighboring bubble universe. The inflating space between here and there expands faster than any message could travel, which means the barrier is not a matter of patience or funding. It is physics. A civilization 1,000,000,000,000 years more advanced than ours runs into the same wall. The horizon is not a technological problem. It is a geometric one, and geometry does not care about ingenuity. This creates a genuine crisis for the scientific project, and physicists are not shy about saying so. Science works by making predictions and then checking them against reality. You propose something, you test it, the universe tells you whether you were right. That loop is the whole engine. But when the thing you are proposing exists permanently beyond any possible observation, the loop breaks. There is no experiment to run. There is no data to collect. The universe simply will not answer. So the question becomes harder than it looks. Is a theory that cannot be tested still science? Some of the most respected physicists alive say yes. Their argument goes like this. The multiverse is not a wild speculation invented from nowhere. It is a direct consequence of theories: inflation, quantum mechanics, string theory, that have been tested extensively in the parts of the universe we can reach. If you accept those theories, the multiverse follows almost automatically. Rejecting it would mean inventing a reason for inflation to stop exactly at the boundary of what we can observe, which itself would require an explanation. The multiverse, they argue, is the honest prediction of accepted physics. Dismissing it because it is inconvenient is not a scientific instinct. It is an aesthetic preference. The other side is just as serious. Physicists like Paul Steinhardt, who actually helped develop inflation, have argued that a framework producing an infinite number of unobservable universes with every possible set of physical laws has effectively explained nothing. If your theory can produce any outcome, it cannot be falsified. And a theory that cannot be falsified is not a scientific theory in any meaningful sense. It is metaphysics wearing the clothes of equations. The word they use is not flattering. They call it a multiverse of the gaps. Both camps have a point. That is what makes this uncomfortable. What keeps the debate alive is a thin thread of hope, the possibility of indirect evidence. Not proof, but fingerprints. The most discussed candidate is something called a bubble collision. If our universe is one bubble in an eternally inflating sea of bubbles, then in the very early moments of our existence, a neighboring bubble might have grazed ours. Two expanding spheres, each a universe unto itself, brushing against each other at the edge. The physics of such a collision would have left a mark, a subtle imprint in the cosmic microwave background, a circular pattern of slightly different temperatures stamped into the oldest light we can detect. Cosmologists have looked. There are cold spots in the CMB that have attracted attention. One particularly large anomaly in the southern sky that some researchers have flagged as a possible candidate. So far, nothing has cleared the bar of statistical significance. The cold spots have mundane explanations that fit standard cosmology. The fingerprint, if it exists, is buried beneath the noise, and we may not have the resolution to pull it out. That is probably the best shot we have. And it is a long shot. There is something almost dizzying about sitting with this honestly. Humanity has built telescopes that can detect a single photon from a galaxy billions of light years away. We have mapped the structure of the early universe to a precision of 1 part in 100,000. We cracked the atom, decoded the genome, landed machines on other planets. And the question of what lies past the final edge of the observable universe might simply stay unanswered. Not because we have not tried, not because the technology isn't there yet, because the universe physically forbids the answer from reaching us. Some physicists find this freeing. The horizon is an honest acknowledgement of our situation. We are not at the center of everything. We are not at a special place. We are inside a bubble of visibility, surrounded by a much larger reality that is not obligated to be knowable to us. The laws of nature were not designed with our curiosity in mind. They were not designed at all. The fact that we can understand as much as we do from inside this small lit sphere is remarkable. The fact that the sphere has a wall is not a betrayal. It is just geometry. Others find it genuinely frustrating. The entire arc of science has been a story of pushing back the boundaries of the unknown, and the cosmic horizon is a boundary that does not push back. Every other wall has eventually yielded. This one is built from the speed of light and the age of the universe, and those are not negotiable parameters. What is clear is this: the theories are real theories, constructed by serious people using the best tools available. The evidence that inspired them, inflation, the flatness of space, the uniformity of the CMB, is real evidence. The multiverse is not science fiction. It may also not be science in the strictest sense. It exists in the strange territory between, and we do not yet have a word for that territory that everybody agrees on. The universe is not keeping secrets out of malice. It is keeping them out of geometry, and geometry does not negotiate. At some point in a conversation about what lies beyond the observable universe, physics quietly hands the question off to philosophy, and the handoff is not a failure. It is an honest recognition of a boundary. Physics is extraordinarily good at telling you what it cannot do. That is actually one of its strengths. The uncertainty principle does not say we haven't built a precise enough instrument yet. It says the precision you want is forbidden at a fundamental level by the structure of reality. The interior of a black hole past the event horizon is not merely hard to observe. Anything that falls in cannot send information back out, ever, by any means. The singularity at the Big Bang is not a moment we have failed to reconstruct yet. It is a place where the equations that describe the universe break down completely and return nonsense. Physics runs into these walls with some regularity. The cosmic horizon is one more wall of the same kind. Not a technological problem, not a funding problem, a law. What makes the horizon different from those other limits is the scale of what sits on the other side. The uncertainty principle governs the behavior of particles smaller than atoms. The black hole interior hides whatever happens inside a collapsed star. These are bounded regions of ignorance. The horizon, though, is hiding something that is almost certainly larger than everything we can see, possibly infinitely larger. The unobservable universe is not a footnote to the observable one. It may be the main event, and we are the footnote. Here is what makes that genuinely strange. We have no way to characterize what we are missing. When you don't know the answer to a specific question, you can at least frame the question. You know what you're looking for. But the region beyond the horizon could contain structures, phenomena, or configurations of matter that have no analog anywhere in the 46 billion light-years we can check. We wouldn't know to look for them. We couldn't frame a question about them. The shape of our ignorance is itself hidden from us. This matters in a way that goes deeper than curiosity. Every physical law we have was derived from observations made inside this bubble. Every equation, every constant, every framework, from quantum mechanics to general relativity, was built by measuring things we could actually reach. That process has worked astonishingly well. The laws of physics we have derived here on Earth seem to hold in galaxies billions of light-years away, to the limits of our observation. That consistency is genuinely remarkable. But it is consistency within the observable universe. It tells us nothing, definitively, about whether those laws hold everywhere. There are physicists who take this concern seriously, and others who dismiss it. The dismissers have a reasonable point. The CMB looks the same in every direction. The same spectral lines appear in the farthest galaxies we can detect. The evidence for uniformity is strong, but strong evidence within your observation window is not the same as proof that nothing changes outside it. A scientist in a single city could observe that the boiling point of water is 100 degrees Celsius everywhere she checks, and she would be right about every data point she gathered and still wrong about Everest. There is a version of this problem that physicists call systematic bias. When you can only observe from one vantage point, your models will be shaped by that vantage point in ways you cannot fully account for. The observable universe is not a random sample of all possible universes. It is the one we find ourselves inside. The constants that govern its behavior are the constants that produce something complex enough to contain observers asking questions about constants. That circularity is uncomfortable and real, and it means our physical laws might describe a special case rather than the general rule. The uncertainty principle, the black hole interior, the Big Bang singularity, each of those limits is a place where our best theories fail or stop. The horizon is different. Our theories don't fail there. They simply have no data to work with. That is in some ways a quieter problem, and in other ways a more unsettling one. A theory that breaks down at least announces itself. A theory that has never been tested beyond a certain range doesn't announce anything. It just sits there, confident and untested, describing the bubble. Some physicists argue this is fine. The observable universe is what we can interact with, what we can affect and be affected by. Science is about the measurable, and the measurable ends at the horizon. Build your models on what you have. Others push back and argue that a theory of everything that only describes the everything we can see is not really a theory of everything. It is a very good local approximation, and confusing local approximations for universal laws is the oldest mistake in the history of science. People thought Newtonian mechanics was complete once too. None of this makes the physics we have wrong. It makes it bounded. That is a different thing. The equations still work here. The predictions still hold within the observable sphere. But the question of whether they are describing something universal or something parochial remains genuinely open, and it may be permanently open, given that the evidence needed to answer it is on the other side of a horizon that no signal will ever cross. The physics we have is the physics of the observable universe, built entirely from observations made inside a 46 billion light-year sphere, and we have no guarantee that it describes anything beyond it correctly. The 3 dimensions of space we move through, length, width, height, are the only spatial dimensions most humans will ever think about, and there is no particular reason to believe they are the only ones that exist. String theory, the framework physicists developed in attempting to unify gravity with quantum mechanics, requires extra spatial dimensions to work mathematically. Not 1 extra dimension, not 2. Depending on the version of string theory you are working with, somewhere between 6 and 7 additional spatial dimensions have to be hiding somewhere. The question physicists have spent decades wrestling with is not whether those dimensions are there, it is where they went. The leading answer is that they are compactified, rolled up, curled into themselves at scales so small that no particle accelerator ever built, and none currently on the drawing board, could probe them. Imagine a garden hose lying on the ground from a distance. From far away it looks like a line, one-dimensional. Get closer and you can see it has a second dimension wrapping around its circumference. The extra dimension was always there. You just needed to be close enough to see it. The extra dimensions in string theory are thought to work the same way, except the scale at which they become visible is believed to be near the Planck length. roughly 10 to the minus 35 meters, which is so far below anything we can measure that it might as well be invisible forever. If those dimensions exist, they are not somewhere exotic. They are here, right now, wrapped around every point in space, including the space inside your own body. What that means for what lies beyond the cosmic horizon is genuinely unknown. The extra dimensions might be compactified identically everywhere, uniform across the entire infinite universe, the same tight little curl at every point, or they might not be. In the eternal inflation picture, different bubble universes settling into different vacuum states could end up with different compactifications entirely, different numbers of large dimensions, different shapes for the curled up ones, different physics as a result. The region just outside our observable sphere might have 3 large spatial dimensions just like ours, or it might have 4 or 2. We have no way of knowing, and no instrument that could tell us. There is a second, stranger possibility that has nothing to do with extra dimensions. Space might have an unusual topology. Topology is not the same thing as geometry. Geometry describes the curvature and shape of space. Topology describes how it is connected. A flat piece of paper and the surface of a cylinder are locally identical. If you stood on either one and looked around, the geometry would seem the same. But they are globally different. On the cylinder, if you walk far enough in one direction, you come back to where you started. Physicists have asked seriously whether the universe might work this way, whether space folds back on itself, whether if you traveled in one direction for long enough, you would eventually re-enter the observable universe from the opposite side. This is not a fringe idea. Several serious topology models have been studied. A 3-dimensional torus, where space wraps in all 3 directions the way a flat video game screen wraps at the edges. A space shaped like a soccer ball. A space with a more complex twist built into its connectivity. Each of these would leave a fingerprint. If the universe wraps back on itself at a scale smaller than the observable universe, the same structures would appear in multiple directions in the sky. The CMB, with its fine temperature fluctuations mapped in extraordinary detail by the WMAP and Planck satellites, would show repeated patterns, matching circles, echoes. Physicists looked for exactly these signatures. They ran careful searches through the CMB data for the telltale repetition that a compact topology would produce. Nothing turned up. If space does fold back on itself, the scale at which it does so is larger than the observable universe, which means we cannot detect it, which means we are back to not knowing. That result is worth sitting with. We check the entire sky with the most sensitive instruments ever built. We looked for the universe repeating itself inside our observable sphere and found no sign of it. And the honest conclusion from that is not that the topology is trivial. It is that if there is a repeating structure in space, the universe is simply too large for us to see it fold. The echo is there. We just cannot hear it. Remnants of earlier cosmic phases are a third category of strange geometry that might be lurking beyond the horizon. Some cosmological models allow for what are called domain walls, boundaries between regions where the universe settled into different vacuum states after inflation. These would be physical surfaces, potentially enormous, separating zones of space with different properties. Inside our observable sphere, no such wall has been detected, but the absence of a wall inside 46 billion light-years says nothing about whether one exists at 50 billion light-years, or 500 billion, or farther. Put all of this together, and the picture of space beyond our horizon gets genuinely strange. We know the geometry is flat inside our sphere. We know there are 3 large spatial dimensions here. We know the topology appears trivially simple at scales we can probe. Beyond that, the constraints evaporate. The rules we have confirmed apply to the region we can observe. They are not guaranteed to hold in every direction forever. The universe we have mapped is a small, quiet, regular-seeming patch, and the question of whether the larger structure is equally quiet, or curved, or folded, or higher dimensional, or threaded with domain walls from a phase transition we will never see. That question is open in a way that cannot be closed by any observation we are currently capable of making. What the universe looks like geometrically past the last reach of our instruments is an open question, and the range of possible answers includes things for which we do not yet have words. Step back from the theories and the numbers and the competing models, and there is a simpler way to say what we have been working through this entire time. Go outside on a clear night, pick any direction, look up. What you are seeing is a bubble, a sphere of light that managed to reach you before the universe got too big for it to finish the trip. Everything beyond that bubble exists. It is not hypothetical. It is not a gap in the math waiting to be filled in. It is just out there, silent and unreachable, separated from your eyes by a speed limit that nothing in physics can break. The horizon you are staring past is not a wall someone built. It is a consequence. Light is fast but finite. The universe is old but not infinitely old. And those 2 facts together draw a circle around every observer in existence. You happen to be one of those observers. So does every civilization that has ever existed or will ever exist, anywhere in an infinite cosmos. Every single one of them is standing inside their own bubble, looking out at their own horizon, unable to see past it. That is the thing that tends to get lost in conversations about the edge of the observable universe. People hear the phrase and picture something like the end of a map, a place marked with dragons, or a boundary beyond which the parchment runs out. But the horizon is not out there somewhere waiting to be reached. It moves with you. Take a spacecraft and fly toward the edge for 1 billion years at close to the speed of light. And when you stop, you will still be at the center of an observable sphere exactly the same size as the one you left. The horizon will have retreated in front of you the entire way. You cannot approach it. You cannot stand at it and peer over. It is not a location. It is a relationship between you and light, and it follows you everywhere you go. What the discovery of the cosmic horizon actually represents is not a failure. That framing gets it backwards. It took centuries of careful observation, the invention of general relativity, the measurement of expansion, the detection of the cosmic microwave background, and the construction of satellites precise enough to map temperature fluctuations smaller than 100,000th of a degree. All of that just to understand why we cannot see further. That is not a defeat. That is one of the deepest things science has ever worked out. We know the shape of our ignorance. We know its size. We know exactly why it exists and can describe its geometry in equations that have been tested and confirmed repeatedly. Most limits on human knowledge are vague. This one is precise, and precision is a form of understanding. The question the whole script has been circling is what actually exists past that edge, and the answers stack up in layers. The first layer is the conservative one. More universe, roughly like ours, running on the same physics, containing galaxies and stars, and whatever happens to be orbiting them. The CMB says the universe is uniform at large scales, which means the region just beyond our horizon almost certainly looks like the region just inside it. Structures we recognize, rules we already know. The second layer is stranger. If space is genuinely infinite, and the flatness measurements strongly suggest it is, then the matter out there recombines into every possible arrangement infinitely many times, including this one, including you. Somewhere in an infinite flat universe, the configuration of particles that produced every moment of your life has repeated, will repeat, and is repeating right now, too far away to ever interact with this copy. That is not poetry. It is combinatorics applied to infinity. It has an unsettling mechanical quality that no amount of familiarity makes feel less strange. The third layer is where the physics gets speculative, but not careless. Eternal inflation, if it is correct, means the space beyond our horizon is mostly still inflating, a churning background in which other pockets have stopped and collapsed into their own big bangs. Other universes, each one potentially enormous by any measure we have, each one potentially running on different physical constants, with different particle masses, different forces, different outcomes. The string landscape suggests there are something like 10 to the 500 versions of the underlying physics available, and eternal inflation may have sampled most of them. If any of this is right, what exists past the final edge is not just more of the same universe. It is a collection of outcomes so large and so varied that the word universe, in the singular, stops making sense. And then there is the layer that physics cannot reach at all. Beyond the cosmic event horizon, information does not travel slowly. It does not travel, not ever, not with infinite time and infinite technology. The accelerating expansion of space has permanently severed the connection. Whatever is out there past that absolute boundary is not observable in principle, not just in practice. We built our entire picture of physical law from observations made inside this sphere, and we have no guarantee those laws hold beyond it. We cannot check. The physics we use to reason about what might be out there was derived from data collected in here. That is a constraint serious enough that some physicists think the whole project of theorizing about regions beyond the event horizon is not science. Others disagree. Nobody has settled it. What is honest is this: the universe almost certainly extends far past everything we can see, in every direction, without an edge. It may be populated by observers exactly like us, sealed inside their own horizons, looking out at their own unanswerable silence. They cannot contact us. We cannot contact them. Each bubble is its own complete epistemic universe, surrounded by a reality it cannot access. The horizon does not mean nothing is there. It means the news will never arrive. The horizon is real. The silence beyond it is real. And somewhere on the other side of both, the universe keeps going.